So we're going to get started on the review for exam 6, chapter 17. The book uses a name for this chapter about that long. Basically, what we're covering is chemical thermodynamics. So I'm going to be working from both versions 1 and 2 of the review document. And let's see, and I've got it identified here. So because the numbering system changes. So version 1, we're going to go down to number 9, I believe. Pick that one up. All right. Number 9. At 1 atmosphere, liquid water is heated above 100 degrees. So we've got a pressure of 1 atmosphere, which is standard pressure. And a temperature is greater than 100 degrees C. That means we're above the boiling point. Recall that when, remember this relationship, change in entropy, the total change in entropy, that is the system and the surroundings together, is equal to system. Remember, if I don't write system in here, it's automatically system. But if it's surroundings, I'll write surroundings in there. So this situation is true. We just add the entropy for the system and the entropy for the surroundings and get the entropy total. Well, at any phase change, when you go from, say, solid to liquid or liquid to gas, in these places right here,
It's an off-year special election.
the total change in entropy is 0. In other words, at equilibrium, at the boiling point, at the freezing point, or the melting point, this is always 0.
We look for longness.
But when you increase the temperature above 100 degrees, then you're not at equilibrium anymore. In fact, you're in a situation where you have, like, if we do like this, surroundings. We're in a situation now where the system is getting more heat than it needs to phase change. So this Q is positive, and we're increasing the energy entropy of the system. That means we're decreasing the entropy of the surroundings. So this value, we have an endothermic situation here. All right. So what effect does that have on the surroundings? Well, if it's endothermic, that means the surroundings has to be losing energy. And in terms of entropy. So the value here for delta S for the surroundings has to decrease. So that means delta S surroundings is less than 0.
You understand?
And that would be, the answer for that one would be B. Now, 10 is related to this one. If the liquid is heated above 100 degrees, what is the delta S for the universe? Well, now we're not at equilibrium, right? So before, at equilibrium, the delta S was 0. But now we're actually increasing the entropy of the total by going beyond equilibrium. So now this value is positive.
You get there.
Now, there's a convention here. Let's see. Delta S for the universe.
Press it.
I rarely ever reference universe as the whole universe. That's only for the definition of the second law of thermodynamics. Every other time when we speak of delta S for the universe, and the authors do this too in your textbook, delta S for the universe is actually delta S total. All right. How about number 11?
No, I got a request. Say that that's what they can.
I was trying to get Charlotte on.
And it sounds good.
What do you want?
Kathy's here.
Okay.
All right.
Flashes the
Let's
clouds.
see. Here we go. All right. So number 11. Which of the following is true? Well, let's look at our selections. Let's see. Got stuff in the way here. I'll just read it from the screen. So our choices are, they all begin with by spontaneous. By spontaneous, we mean. So when we say spontaneous, we mean a process that proceeds without any outside intervention. Non-spontaneous would be the other direction, where you have to force the system to go backwards, so to speak. But when we say spontaneous, we're referencing from left to right. Okay, so now let's see which one of these fits the spontaneous definition. By spontaneous, A, we mean that the reaction of the process will always proceed to the right, as written, even if very slowly. Well, that's true. Let's see, do the others say that also? B, always proceed to the, no. B will not proceed to the left. C will not proceed to the left. D proceeds to the right. So A and D at this point, A and D are possibilities, because proceeding to the right implies spontaneity. Okay, so let's see what the difference between A and D is. So A says, after that, increasing the temperature may speed up the reaction, but it does not affect the spontaneity of the reaction. And D says, increasing the temperature may speed up the reaction. Both of those are true. It generally affects the spontaneity. All right, here's where you go for the answer. Delta G equals delta H minus T delta S. The Gibbs equation. Remember, for this to be spontaneous, that value must be negative. So, if we have a balance here between enthalpy and entropy, there's the influencer, temperature. Temperature does have an effect on spontaneity. Because if let's for example say we have an exothermic reaction, delta H equals a negative. Okay? And if delta S is positive, then this reaction as written would be spontaneous no matter what the temperature is. But if delta S happens to be negative, then this would only be spontaneous if temperature was very, very low, because that would make the outcome here positive. And it would have to be very small in order to keep this one negative and the overall be negative. So temperature does have an influence on that reaction. And also, if delta H is positive, then in order to make this one negative, delta S would have to be positive, and that would have to be very large. So temperature does have an effect on the spontaneity of a reaction. That's why D is the best answer for this question. We're just getting started. I'm in version 1. Let's see. I skip a bunch of them. I skip around a lot. Let's see. Down in the 30s, I think, is where I'm headed. There we go.
You'll post this on the YouTube.
Oh, yeah. Sure. So for the following reaction, carbon dioxide and water is in equilibrium with methane and oxygen. Say CH4 plus oxygen gas, and it gives us a delta H of, let's see, I have to read it up there, 803 plus 803 kilojoules. Okay, you didn't miss much. All right. Okay, so what are the questions? Which of the following will increase K? So if we're going to increase K, right, if K is increased, what does that mean for our calculation? Well, that means CH4 and O2 squared over CO2 and H2O squared would also have to increase. What that means is this part of the equation would increase and maybe this one would stay the same or decrease. Well, it had to decrease if we're playing a balance game. That one would have to get larger, this one would have to get smaller in order to change the K in that direction. So that means the equilibrium would have to shift to the right. Okay. Okay. So if we look at our choices, A says to decrease the number of moles of methane. If you simply decrease the number of moles of methane, what is that going to do to the equilibrium? Nothing. The only thing that affects equilibrium is temperature. And I'm saying that in terms of the K. The K is only affected by temperature. So we can discount any of those that have nothing to do with temperature, right? Decrease the number of moles of methane, increase the volume of the system. Now, they will affect the equilibrium position, but they won't affect the equilibrium constant. We want to change the constant. So we have to change the temperature. And by process of elimination, C probably looks like the best answer. But does it say what we need? Or do we need to go to E and say none of the above? So what happens if we increase the temperature? Well, we know that this reaction is endothermic. That means the heat term is on this side. Okay? So if we look at Le Chatelier and say, all right, if we increase the temperature, we're putting energy in here, we're shifting the equilibrium and the constant to this side, that will increase the products, increase the numerator. That will, increasing the temperature will shift the K higher. Right? Now, in your worked problems, I give you an alternative way to look at this by calculating the actual Ks, and we go through a bunch of mental gyrations to end up at the same location. And actually, I use the, let's see, I forget the name of that equation. Okay. Oh, that's the Van Hoff equation. Anyway, you don't actually have to use it to answer the question. Once you know that the heat term goes on this side, and you take into account that the equilibrium constant does not change if we change the amounts or the volumes. Only the position changes. The K only changes with temperature. Then we look at temperature and see, okay, does the increasing temperature shift to this side to give us that more product? Yeah, it does, because it's endothermic. And that will answer the question as C. Okay. 36. All right, consider the gas phase reaction, NO 1/2 O2. So all of these are gases. N2? No, O2, excuse me. O2 in equilibrium with NO2. And what else are we given? Delta H is negative 5691. Delta H0 is negative 56.1 kilojoules. And delta, and K is given, excuse me. K. So I can read it from here better. 1.46 times 10 to the 6th at 25 degrees. Okay. 25 degrees C. And that's only important for coordinating this with standard conditions. Those are standard conditions. Okay, now what's the question? What would be the effect on the amount of NO present of compressing the equilibrium system to a smaller volume while keeping the temperature constant? All right, if we're going to keep the temperature constant, then that value will not change. That's the equilibrium constant. And if we're keeping the temperature constant, it will have no impact on that either. Right? We know it's exothermic, but we're not changing the temperature, so we can ignore it. Right? Just blue smoke. So if we look at it in those terms, compressing the system, we want to use Le Chatelier. So we have 1 mole here of gas, and over here we have 1.5 moles. So when you compress the system, how is it going to respond? It's going to try to relieve that pressure by decreasing the number of moles. Okay, remember, if you put more moles into a same volume, or if you decrease the volume, then you're going to increase the pressure. So we relieve the pressure by decreasing the number of moles. We're going to shift to the right as written. So the amount of NO will decrease. Right? B should be the answer to this one. There's a lot of superfluous information there. With a different question, maybe you would need those. But for this question, you don't need those. Let's see, I gotta go down. Okay, here we go. 46. All right. Given the following data, calculate the normal boiling point for formic acid. All right, what is formic acid? That. And it's going to be in equilibrium. If it's boiling, we start at liquid and we go to gas. Okay. Now, let's work this backwards. Since we're given enthalpy and entropy, and we know that we know this fact, this equation, delta S surroundings equals negative delta H over T. At equilibrium, delta S for the system is just change the sign. Why? Because delta S total is 0. And that means if we add this one to this one, they have to cancel. So at the phase change, we can say this. Okay, so if we want to find out this value right here, the boiling point, we need to know both this one and that one. Okay, so the information given should be enough. what we need is to say for delta H0 equals the sum of the delta H for the product minus the sum of the delta H's for the reactants. Right? So that means we look at our information, and remember these are in kilojoules, and delta S is in joules. So we're going to have to change some units once we get there. I won't let you forget that. Okay, so product is gas. So the gas is minus 363, and that's kilojoules. And there's only one of them. And then minus whatever the reactant has to be, which would be minus 410. Okay. So I'm not going to rely on calculating this in my head. This is going to be a positive. Right? Negative times a negative positive. And then 363 minus that is positive 447 kilojoules, which is equal to what? 47,000 joules. Okay. Delta S0 is a similar format. We just need the product delta S, which is gas, 251.1 joules, minus the reactant, which is the liquid, 130 joules. Okay. So 251.1 and 130. This is 121.1 joules. All right. Now that we know this is for the system here, this is for the system. Whenever I don't write system down here, that means system. If I write total or surroundings, then that identifies it. But if I don't write it, that means system. So solve for T. T then would be delta H0 over delta S system. Right? So delta H0 is 47,000 joules and 121.1. So I just divide those and I get, let's see. That's not right. That's right. Forgot to change it in my calculator. 388 K. Now, is the temperature? No, temperature's in C. So minus 273 equals what? 115 degrees C. 115 degrees C is the boiling point for formic acid. Okay. There were a lot of steps there, but that's the nature of the beast. It's 2. Okay, calculate the delta G for water plus oxygen yields hydrogen peroxide at 600 K temperature using the following data. All right. I think I know where I'm going with this, but I don't want to waste any time. I want to be sure I'm headed in the right direction. Okay. We're given 2 equations with their K's. And do we need to calculate the K for that reaction? Well, if we want to find the, where is it? Using following data. Delta G 0. Right, so what is delta G 0 in this case? Well, the information we're given is in terms of equilibrium constants. So we do have a relationship between delta G and K. It's negative RT log K. Okay, so if we can find out what that K is for the reaction as given, then we can calculate delta G. So if our target equation is this one, H2O gas plus 1/2 O2 gas yields hydrogen peroxide gas at 600 K. 600.1 K is the temperature. All right. We're given these other two. If we use the first one as is, that puts H2O2 on this side, which is where it needs to be. So H2 gas plus O2 gas yields H2O2 gas. And the K for this one is 2.3 times 10 to the 6th. And this is at the same temperature, so we're good there. All right, so that gets this one here and here. The other one has water on the wrong side. So if we put water on this side, and that would be equal to 2 hydrogens plus the oxygen, right? Oxygen. Okay, we flip the equation. So that means the K has to be inverted. Right, so for the K for this one is equal to the new K is the old KP inverse. So we would have 1 divided by 1.8 times 10 to the 37. Okay. Now, here's the problem with that. We only need 1 water. Right? So we actually need to take 1/2. Let's see, what is that? What happens to the KP when you multiply times a value here? That becomes the power. Right? So if we do that, then we actually have to take square root of it, 1/2 power. Okay, now does that give us what we need? That would be 1. This would be 1, and this would be 1/2. Okay, if we add those together, is that going to give us what we want? Well, we've got an O2 here and 1/2 O2 there, right? So that cancels this one and leaves us with 1/2 O2 on this side. That's good. This one as is. Okay. So we got that one, take care of that one. This is 1 hydrogen here, 1 hydrogen there. They're gone. And we've got 1 water. Okay, so I think we've got, yeah, we just need to what? You multiply the K's together. So what we've got here is 2.3 times 10 to the 6th times the square root of 1 over 1.8 times 10 to the 37. All right, so that's our new K. KP double prime. All right. So let's see, I'm gonna take the inverse of 1.8 37 power And let's take the inverse of that and then take the square root of it. And then multiply it times 2.3 times 10 to the 6th. And that I get 5.42 times 10 to the minus 13. You get that? Okay. So now that we have the K, we can plug the K in here. So minus R is 8.3145. And T is already in Kelvin, 600.1, times the log of our K double prime. So I've already got that one in here. So I want to take the log, the natural log of it. I get minus 28.2 times 600.1 times 8.3145. And that's a negative. A negative? Yeah. 1.4. That's only two significant figures, so I have to stop it there. Times 10 to the 5th. Delta G zero. Oh, excuse me. This is in joules. So take 1,000 out of that, which is minus 1.4 times 10 squared kilojoules, or minus 140, right? Kilojoules. 141? Okay. Yeah, I must have kept that one in there like that. I don't know why, because that's only two significant figures. Best answer. Choose the best answer. Okay. That wasn't too bad. Just had to.
Now,
Yeah.
the answer is A, right? So what happened to the negative sign?
Oh. Yeah, what happened to the negative side? Good question. Let's see. Okay. Wasn't supposed to be a negative sign there. I forgot when I did the delta G zero equals negative RT log K.
Okay, so that negative.
This one gives you a negative. I forgot to multiply it by that negative
Negative.
to give you a positive. Yeah. So it should be a positive value, which means what? That's not spontaneous. Because delta G zero, not at that temperature. It's spontaneous in the other direction. It'll decompose into oxygen and water spontaneously. Okay. Next 53. Let's see. Okay. I think this one's gonna take some work, so we got to be methodical about it. Consider this reaction: 2NO2 gas and O2 gas is in equilibrium with N2O4 gas, I believe. Yeah. Delta H is minus 56.8 kilojoules. Delta H minus 56.8 kilojoules. And delta S is minus 175 joules per K. Okay. That's given. In a container at 298. So 298 is 273 plus 25, which is standard temperature. That's good. N2O4, at that temperature, N2O4 and NO2 are mixed with initial partial pressures of 2.4 atmospheres. N2O4 is given first. 2.4 atmospheres. And 0.42 atmospheres. Okay. Which of the following statements is correct? Some N2O4 will decompose in the NO2. Some NO2 will dimerize to form N2O4. System is in equilibrium. Okay, if we're going to determine equilibrium, we got to compare the K with the Q. We can calculate the K expression here is going to be N2O4 over NO2 squared. So the Q calculation, we can do that right now. We just need 2.4 atmospheres divided by 0.42 squared. But we're still going to have to calculate the K. 2.4 enter 0.42 squared. Divide that into it. So this is 13.6. Okay, this is what we need to find out. Okay. So what expressions do we have that are that deal with K? Right. We know that delta G zero equals at equilibrium, right? We're headed for K, so we have to go for standard conditions. Negative RT log K. And we also know that delta G equals delta H minus T delta S. Because in order to solve for K, which we need here, we also need G. And this will give us G because we have delta H and delta S. So we're going to do these at standard conditions. And why don't we combine these equations? Then we can just do one calculation. So if A equals B and B equals C, then A equals C. All right, so if both of these are equal to delta G, minus RT log K is equal to delta H 0 minus T delta S 0. And we want to solve for K. So log K equals delta H 0 minus T delta S 0 divided by negative RT. Okay, we're at standard conditions. We have to assume that because that's all we're given. We're only given standard conditions. All right. So if we plug the values in here, delta H is, and these have to be in common units, and the units are determined by that R. 8.3145 is in units of joules. So 56.8 kilojoules would be minus 56.8 times 10 to the third joules for delta H. And then minus T, well, T is 298 at 25 degrees. 298 K times delta S, which is minus 175 joules per K. And then we'll divide by negative 8.3145 and 298. Okay. And that should give us log K. So let's see, 56 exponent 3. Let's see, let's go back. Let's change the sign. Then exponent. And then 298 times minus 175 will be a positive. 298. Then I'm gonna combine that term with this term. Okay, and then I'm going to divide by 8.3145. That's a negative. And then 298. Okay, so I get K is 1.5 log K. So what's K? Remember, e to the 1.55 power. Like that, and I get 4.73. Okay, so K, we determine K to be 4.73. Well, if the Q is 13.6, that means it's too big. We've got too much of this, right? We got too much product. That means it's going to shift to the left. And that means we're going to decompose N2O4. Some N2O4 will decompose into NO2. That's A. Okay.
Is that because K is smaller than Q?
Yeah. Q, since Q is bigger than K, that means we have too much product to start with. That means it's got to shift this way in order to reach that value. We got to make the product side smaller in order to make this smaller in order to go to here. Okay. Okay.
I'm writing down your explanation.
Oh, okay. Okay. Let's see. It was 53, 56. And we're still in version 1. Consider the following system at 25 degrees, standard temperature. PCl3, gas, plus Cl2, gas, yields PCl5. I believe that's right. Delta H is minus 92.5. Delta H minus 92.5 kilojoules. Okay, that's everything that we're given. So if the temperature of the system is raised, the ratio of the partial pressure of PCl5 to the partial pressure of PCl3 will be. Okay, so we're looking for the ratio of the partial pressure of PCl5 to the partial pressure of PCl3. It's not quite the K value because we left this term out. But it's also going to tell us which way the reaction will shift. So the temperature is going to be changed. Right? That means that if we're at equilibrium, we're going to get shifted. So we needed to incorporate this term because we're messing with the temperature. So minus 92.5 means delta H is on this side. Okay. Now we can say something about the temperature. If we increase the temperature, temperature of the system is raised. We're going to shift back this way, which will decrease this one and increase this one. So the ratio, when we do that, is going to decrease because we're decreasing the numerator, increasing the denominator. So we should get a decrease in that ratio, which would be B would be the best answer. Okay. All right. Oh, we got another one. Okay. I put a note in here. So we're gonna do 58. Okay. Why did I say go to number 56 in version 2? Probably using the same equation and scenario with a different question. That's my guess. So let's get 58 done. And then we'll skip to version 256 and see what that tells us. Okay, the equilibrium constant, Kp in atmospheres for the dissociation reaction of Cl2 to 2Cl. Cl2 to 2Cl. Whenever I see something like that, I say, that has to be gas. No other alternative. Kp was measured as a function of temperature. Okay, so we've got K values at different temperatures versus temperatures. A graph of natural log Kp versus inverse, inverse of T. Okay. Gives a straight line with a slope of minus 1.651 10 to the 4. 1.651 times 10 minus 4. That's equal to the slope. And a y-intercept of 14.51. Okay. All right, so what's the slope? Well, if we go to the Van Hoff equation, we get natural log of K equals negative, negative delta H 0 over R times that one, plus delta S 0 over R is the intercept. I think that's right. Yeah. Okay, so if that's what this line represents, what's the question? For these data, which of the following statements is true? The reaction is exothermic, endothermic. The reaction rate is high. This is equilibrium. It says nothing about the rate. We have no indication of activation energy in this equation. Reaction is not spontaneous. Well, well, let's look at the others first. Exothermic, endothermic. All right. So which one has the delta H in it? This term right here. This is equal to negative delta H 0 over R. Right? So these negatives cancel. And we have R of 8.315 times this value. Right? So what's delta H? Well, we could multiply this one times that one, take the negative over there with us, that gives us a positive value. So delta H is going to be positive. That's endothermic. Right? Yep, that's endothermic. So we found the answer. Let me see, do I make any more comments about that here? No, I go straight to endothermic. Okay. Oh, now we want to go, let's go down to version 2, number 56, and see what that has to do with everything. It should be in the same document here. See. Okay, yeah, those same conditions. The value of delta H for this dissociation reaction is, okay. So all we need to do here is calculate delta H let's see, it doesn't say delta H zero. Come on. I think it's back here. Six. All right. So it was a typographical error. Because we can get delta H zero out of this. But we can't get delta H because we don't know other conditions. All right, so 8.3145 times that value. 65. Is 1.37 times 10 to the minus third. Let's see. This is going to have to be in joules, isn't it? Oh, wait a minute. This is a positive form. Let's do that again. Yeah. I misread. 1.651 exponent 4. So this is to the fifth joules, or 1.37 times 10 to the squared kilojoules, or 137 kilojoules. There we go. B. Okay. Excuse me. So now we can go back. This was version 2, number 56. Is this calculation right here. Now I'm gonna go back up 58 and see if there's anything left. Let's see. Yeah, we got a number 59. That would certainly be weak. Okay. For a certain process at 300K, 300K equals temperature. Delta G is minus 10.4. G equals minus 10.4 kilojoules. And delta H is minus 7 kilojoules. H minus 7 joules. If the process is carried out reversibly, the amount of useful work that can be performed. Oh, the amount of useful work that can be performed, that means maximum. Maximum work that can be performed equals delta G. All right, so the answer is minus 10.4 kilojoules. Okay. E there is reversibly. Oh, okay, now we're into version 2. Change that. Version 2. And we're at number 2. Okay. A 2-bulb flask contains 5 particles. Right. Five particles in here. 1, 2, 5. Okay. What's the probability of finding all 5 particles on the left side? This is a probability problem, statistical problem. Let's look at it 1 particle at a time. What's the probability of finding one of those on the left-hand side? It can either be on that side or this side, right? So the probability is 1/2. Okay. What's the probability of finding 2 on one side or the other? It's also 1/2. And we could go for 3 and 4 and 5. So the probability of each one of them being on one side or the other is 1/2. The probability of 1 and 2 both being on the same side is 1/2 times 1/2. So it's 1/4. 1 and 4 is the probability for both 1 and 2 being on the left-hand side. For 3 of them, it's 1/2 times that, because you got 3 to deal with now, and 4 of them, and 5 of them. So actually, it's 1/2 to the 5th power. Is the probability of finding all 5 of them on the left-hand side. And since the answer is given in percent, we got to say, what is 1/32? Inverse of 32 times 100 is 3.1, or let's see, 3.13, I think it says. 3.13% of the chances of finding all 5 on the left-hand side. Now, just as I'll give you a freebie, when this is just 5 particles, and it's only 3% chance. So what would it be for Avogadro's number? Right? It would be 1/2 to the 6.022 times 10 to the 23rd power. So it's infinitesimally small that you would find them all on one side. I had a professor one time that said, I think he was being funny. He was trying to make a point of statistical probabilities for things being this way or that way. And he says there's an infinitesimally small chance, probability, that all the air in this room will migrate to that corner and will suffocate. And he was right. I mean, it's infinitesimally small, so don't worry. It's more likely that you'll have an equal distribution on either side. That's the higher probability. And that in chemistry, in thermodynamics, we call microstates. All right, let's see. Come on, who's next? There we go, 14. 14, for the process chloroform, CHCl3. CHCl3, what is that? Oh, that's a solid. Is going to CHCl3 liquid. So the delta H for this process is 9.19 kilojoules. That makes sense. It's endothermic. We got to put energy in to make it from a solid to a liquid. Okay. We also given delta S0. Delta S0 equals 43.9 joules per Kelvin. What's the melting point? Okay, We did one like this before, didn't we? Yeah, we did one like this before, where you have delta S. If we're at equilibrium, then delta S for the system is equal to delta H over T. Delta S for the surroundings would be negative delta H, but we're worried about the system. So if we solve for T, that's delta H over delta S. And we have yeah, 9.19 times 10 to the third joules. And then 43. Okay. Yeah. So that's 209 K. And temperature's given in C, so we minus 273 is minus 64 degrees C. Okay. The only reason we can do that is because the system is at the melting point, phase change. Excuse me. 20. In which case must a reaction be spontaneous at all temperatures? Okay, this goes back to the Gibbs equation. So if this is going to be negative, under what conditions will this always be negative? Well, you need a negative term here and a negative term there, correct? So if this is negative, this is positive, then this is always negative because that negative sign at any temperature. So delta S is positive, delta H is negative, which is D. All right. Who's next? Here we go. 26. Okay. When a stable diatomic molecule spontaneously forms from its atoms. Okay, a stable diatomic molecule spontaneously forms from its atoms. And I always go for gas. Remember why? Because if it's not gas, you've got to introduce energy for phase change. So we always take these in terms of gas. Right? So what we're saying is this is spontaneous in that direction. The stable diatomic element is formed from its atoms. So what are the signs of delta H, delta S, and delta G? Delta H, delta S, delta G. Looking for the signs. All right, let's go for delta S first. Well, no, let's go for delta G because the problem says spontaneously forms. This has to be negative. Right? That's the only way you can have spontaneous. The delta H we could approach this two different ways. Is this going to require energy or give up energy? Well, when you go from two separate atoms to a molecule, that's an exothermic process. Right? This is more stable than that side, so it's going to give up heat. And if we're going from 2 moles here to 1 mole here, that's a decrease in delta S. So they're all negative. Now let me see. Let me check myself and see if I gave a different explanation. 26. Yeah, okay, it works. Search.
Why was the delta S negative?
Delta S negative is because you went from 2 moles on the left-hand side to 1 mole on the right. Yeah, you're becoming more ordered, so to speak. I'm at this one. 31. Calculate KSP for the salt, sodium chloride at 25. KSP means that we're going from this to sodium ions in aqueous solution, chloride ions in aqueous solution. And what else are we given? 25 degrees. Standard temperature. Okay. And we have delta G of formation for each one. Okay. So what I'm looking at is, since we're at 25 degrees, I can say this delta G0 equals negative RT log K. Okay. So we can calculate delta G for this reaction because we have the data. We take this one plus that one minus this one. So sodium is minus 262 kilojoules. And chlorine or chloride ion is minus 131 kilojoules. Then we'll subtract the heat of formation for, the delta G formation for sodium chloride minus 383.8. Okay, so that will give us delta G0 for that reaction. Okay, so let's see, 262, 31, and then 383.8 plus. So I get minus 9.2 kilojoules. Is that reasonable? It's about 380. Do that again. 3.8. And then I'm going to subtract 131, 262. Yeah, that's kilojoules. But this R is in joules. So we need minus 9.2 times 10 to the third joules. Now we can put it into the equation. We want to find out what? Yeah, we want to find out what K is for that, KSP for that. So log K is equal to delta G0 divided by negative RT. So minus 9.2 times 10 to the third joules divided by negative 8.3145 joules per K. And then the temperature. 25 or 298. There we go. Okay. 8.345 divide 298. So I get 3.71 times 10 to the minus third equals log K. Then K would be e to that power. Which is 1.0. Okay, what did I do wrong? I did something wrong. Hmm, 31.
Oh, 4,115.
Yeah, I did something wrong. It happened right here. It may be safer to do it this way. Put the delta G here, minus 9,200 equals minus 8.3145 times 298 times log K. And then log K equals 3.714. And K equals, I think, 40. There we go. A math error. Okay. Next. Scroll 34. Wait a minute. We had that point like this before, didn't we? Yeah, this is a duplicate. We did this one before in version 1. How will raising the temperature affect the amount of NO present? Yeah, we did this one before. Yeah, we'll skip this one. I don't know how it crept in when I split version 1 and version 2 somehow this one got duplicated. Okay. This is definition. Second law of thermodynamics states what? Well, remember the first law. First law is delta E for the universe is equal to 0. There's no change in the energy for the universe. Second law, in its simplest form, is delta S for the entire universe, and I do mean universe in this case, is always greater than 0. But it may not be in those words. So let's see. A, energy is conserved. No, we're not talking about energy in the second law. B, entropy of the universe increases during a spontaneous process. Yes, that's a good one. B is a good one. Well, we found the correct one, so E can't be it. Heat content, nope. All these are valid components of snow. Okay. We're stuck with B. B is the only one that works. All right, 43. Is this unique? I think this one's unique. We haven't done this one before. A mixture of hydrogen and chlorine remains unreacted until it's exposed to ultraviolet light from a burning magnesium strip. Then the following reaction occurs. So this reaction here and HCl, okay, it's there. And we need energy. We got to add energy here, and that's from the magnesium strip burning. Oxide. So it's B2 and B2. So that energy supplies the activation energy for this reaction. All right. We're given delta G for this reaction is a negative 45.54. Kilojoules. Delta H, we're given all these values to help us answer this question, minus 44.12 kilojoules. Delta S is minus 476, minus 476 joules per K. Okay. Which of the following is consistent with this information? Well, let's draw a picture. This is progress of the reaction. Probably know where I'm going with this. This is energy. This value here is negative. So that means the reactants have higher energy than the products because this is exothermic. Like that. So the reactants, H2 and Cl2, yields HCl. And this is activation energy. Okay. And this delta H. It doesn't say anything about delta S with that diagram, but what we know from this explanation, well, first of all, this reaction is spontaneous. Right. So we know it's spontaneous. We also know it's exothermic. And when we look at this diagram, remember we can subdivide it into two things. This in the middle is kinetics. And this from either side is equilibrium or thermodynamics. Okay, so we can say two different things about this. One is, how about the kinetics? Right. Well, those reactants are going to sit there in that bulb and do nothing until we give it an activation energy. So what we're saying is that kinetically it's stable. It's not going to move at any rate that's detectable until we give it the activation energy. Right? So it's kinetically stable. We can also say something about the equilibrium or the thermodynamics. In other words, the product has less energy than the reactants. And of course, the reaction is spontaneous because delta G is negative. So which one fits? A says the reactants are thermodynamically more stable than the products. Well, yeah. I guess, yeah, that's true. The reaction has a small equilibrium constant. A small equilibrium constant. Well, the only way to determine that is to do the calculation. Right? Delta G equals negative RT log K. But do we know what delta G0 is? We'd have to assume that. That's the only way we could get there. So log K then would be minus 45.54 times 10 to the third, right, divided by 8.3145. Are we given the temperature? Hydrogen exposed ultraviolet light. No, we have to assume that it's at standard temperature. That's the only way we can calculate this. So 45.54. 3. 5. So this is minus 18.38. Yeah, it's log K. K then. Yeah, and then K would be that 1.04 times 10 to the minus 8. So reaction has a small equilibrium constant. Well, yeah, that's true. The ultraviolet light raises the temperature of the system and makes the reaction more favorable. Now, the ultraviolet light supplies energy, but it's not, it's entering from the outside in a form that is just sufficient to provide the activation energy. It doesn't change the temperature. Negative value for delta S slows down the reaction. Delta S has nothing to do with reaction rates. Delta S is out here. Reaction rates in here. So the reaction is spontaneous, but the reactants are kinetically stable. We're looking for the best answer. The reaction is spontaneous, yes. And the reactants are kinetically stable. Kinetically stable, yes, because they're just going to sit there until we give them the activation energy. All right, so E seems to be the best answer. Right, there are other possibilities, but we're not given a 2 of the above or 3 of the above or whatever to go on. So I would pick E would be the best answer. We have other possibilities, but when we're looking for the best answer, I'm going to go for E. Okay, 52. All right. So the equilibrium constant of a certain reaction was measured at various temperatures and give the plot shown below. What's the delta S for the reaction in joules per mole K? All right, so we look at that plot and we take the Van Hoff equation, natural log K equals negative delta H0 over R times 1 over T plus delta S0 over R. Then how are we going to get at delta S? We need the y-intercept. So delta S0 over 8.3145 is equal to the intercept value, which is 3. 3 is the intercept. So delta S0 is equal to 24, 25, something like that. C? And this would be in joules per K mole. Okay. That's the Van Hoff equation. That's just to see if you know how to read it. Read a graph. Okay, 56. So it warmed up in here. Yeah, it's cold. We have 2 degrees.
It's Virginia spring weather.
Yeah. Yeah, and they apparently they haven't switched over to heat yet. The equilibrium constant Kp in atmospheres for dissociate.
That's the one.
Oh, we already did that one, didn't we? Yeah, we did that one. So okay, skip that one. 57. For a certain process at 300K, it is carried out so that useful work is performed delta G. Okay. Well, if a certain process has a delta G of negative 12.2 kilojoules, negative 12.2 kilojoules. If the process is carried out so that no useful work is performed, what's delta G? Right, so we're saying that the work performed from this process is 0. Remember that's equal to, that's not the maximum work. The maximum work is equal to a delta G. Right, delta G hasn't changed at all. Just because you didn't get work out of it doesn't mean delta G changed. So delta G is still 12.2 minus 12.2 kilojoules. That hadn't changed. That's a trick question. Oh, that's it. All right. So we're done early. Let's see, I got Heather and Kathy, do I have them down?
Oh, I forgot to sign in.
Okay. Don't see her. No, she's not zoomed in either. Okay, so what's on the agenda? We've got coming up next Monday should be the exam on this material. Yes. An exam next Monday, and right after that, I'm going to introduce chapter 18 electrochemistry. And since the following week is finals, we're not going to have time to do a review on this chapter. So you have to review in Brightspace. Well, look at a previous video that I have for chapter 18 review. And then the 6th, that the Monday after next, we'll have the exam. Now, if you can, I don't have any objections if you want to take it on Brightspace, or if you want to come in and do it in person. That's your choice.
That's for the final.
For the final, yeah. Yeah, the final's not comprehensive. It's just on chapter 18. But if, since I don't have time to do an in-person review, if you can, you may want to come in case you have questions. Because it'd be more difficult to take it online, and if you have questions, you kind of stuck.
Here's some.
You have something for me?
Extra.
Oh, okay.
Now, on the lab, like I have like a video right now. I think all of my labs are turning except for the last one. And all the notebooks and stuff, I should have everything.
Oh, yeah, we have a final notebook check too. Right, so for the benefit of our viewing audience, the final notebook check for the lab, you could submit that in Brightspace, but you got to photograph every page that has information on it. You don't have to do every blank page in there. But if you've got like through page 50 with stuff on it, then it's probably more efficient just to do every page, even if you got some blank ones.
So can we bring it in?
Oh, yeah, you
like
can bring.
eggs,
Sure.
I guess,
Yeah.
next exam, like chapter 17 exam.
Yeah, you can bring it in next week, or if you show up for the final, you can bring it in at the final. That's okay.